Welcome back, chemistry students. So today we're going to learn about something called stoichiometry. Now, the word stoichiometry is actually scarier than the actual calculations. So basically, stoichiometry is going to let us move forward from our mole calculations, where we have been talking about one substance and we've converted from particles to moles or moles to mass or backwards, but it's always been about one thing. So stoichiometry allows us to do calculations involving a chemical reaction, and we can now calculate quantities of other substances such as reactants or products. And to do that, we are going to need to use something called the mole ratio, which is going to be our third conversion factor. All right, so mole ratios are just another type of conversion factor, and they come from the coefficients in a balanced equation. So we've already done balancing equations earlier this year, as well as in grade 10. So these numbers here that you use in order to balance an equation are called the coefficients. Okay? So if we use those coefficients, they basically tell us, for every 2 aluminum oxide that you decompose, you're going to end up with 4 aluminums and 3 oxygens. Now, specifically, the 2, 4, and 3 refers to how many moles of each of those substances you're going to end up with. So we can make a whole bunch of different mole ratios from this equation. So here's one. 2 aluminum oxide would yield 4 aluminums. Or we could say 2 aluminum oxides would yield 3 oxygens, is another possibility. Or we could say 4 aluminums could correspond to 3 oxygens. Okay, so, and any of those can be written upside down as well. Okay, so also inverted. So any of those could be flipped, is what we mean. Okay, so those numbers, remember, are coming from here. Okay, now, again, just so it's not so scary, I want to show you that you have been using stoichiometry your entire life in very straightforward types of calculations. So for instance, anytime you're cooking or baking and you want to alter the recipe or figure out how much of something you can make, you're using stoichiometry. So here's an example of baking cookies, and I have a recipe. 1 cup of sugar plus 2 cups of flour, 1 bag of chocolate chips, and we're going to get 24 cookies. I like a lot of chocolate chips. Of course, we're going to have some wet stuff in there, like some butter and water and whatnot, but we'll just keep it simple. So the problem is you want to make as many cookies as possible, and you look in your cabinet and all you have is 1.5 bags of chocolate chips. So you want to know how many cookies you could make. So just like we've been doing, you're going to start with what you're given. So I give you 1.5 bags chocolate chips. Just shorten that up. And we're trying to figure out how many cookies you can get. So the conversion factor between chocolate chips and cookies is that 1 bag of chocolate chips will give you 24 cookies. That is a conversion factor. So we're going to set that up as a conversion factor. And you know from all the work we've been doing that the bags of chocolate chips better go on the bottom because we need to cancel them. So 1 bag of chocolate chips is going to yield 24 cookies. And this is where now we're going to cancel out the common unit, which is going to make you take 1.5 and multiply by 24, and we're going to be able to make 36 cookies, which would be just enough for our class if we had one. So this is our conversion factor. Doesn't look very chemistry-ish, but it's what we're going to be using, only we're going to be doing it with moles. So another just simple everyday example is to do with carpooling. If you and some friends were planning to go to the beach, you might need to know how many people are going to have to drive. And perhaps there's 12 people that want to go, and everyone is driving a vehicle that seats 5 people. So 1 car and 5 people is what will make up a load. So how many cars are you going to need? So we're going to start with what we have. 12 people. And again, I'm sure you could do these questions in your head, but we just want to show that, you've been doing this kind of stuff. So according to our balanced equation, there is 5 people for every 1 load or one car. Okay. So 1 car to 5 people, and we want our answer to be in cars. So we're going to use car on the top. People is going to cancel. 12, you're going to divide by 5, which is going to give us 2.4 cars. Now, of course, we know that cars don't come in pieces, so you're going to have to round it up to a full car. So you're going to need to take 3 cars in order to get 12 people to the beach. And of course, not every car is going to be full. Should just put boxes around our final answers because that is a good practice. Okay, so that's how easy stoichiometry is. Now, we're going to do an example that is with chemistry, and we'll use the same reaction that we have up here, the aluminum oxide decomposing into aluminum and oxygen. So, question is, how many moles of oxygen can you produce from 5 moles of aluminum oxide? Now, the first thing I want to demonstrate is when you are doing stoichiometry problems, it's a really super good habit to start off with your balanced equation written at the top, and you should spread it out across the page because sometimes you're going to want to do some work under it. This question is pretty straightforward, so that's not going to be the case so much, but our next lesson is going to be much more involved. This is just your starter lesson. So 2 aluminum oxide produces 4 aluminum plus 3 oxygen. So I have spread that out just so we're not so squished together. Okay. Now, the next step is you should record everything you know and everything you need right under the balanced equation in the correct spot. And I like to think of every substance, reactant, or product as kind of like a column that you can organize things under. So how many moles of oxygen? So over here under oxygen, I'm going to write question mark moles. Okay, that's what I'm going for. And then I have 5 moles of aluminum oxide. So here's aluminum oxide. So 5.0 moles of aluminum oxide is what I'm given. All right, so once you kind of have your stuff organized, then we're going to see how we can get from this to that. And it's exactly how we did the cookies and car problems, where we're going to have to use our third conversion factor, which is called the mole ratio. So we're going to multiply 5 moles of aluminum oxide by a ratio that definitely has to have moles of aluminum oxide on the bottom. And the thing we want, where you've got your little question mark, is moles of oxygen. So fill in your 2 entities, and then you can look to see, okay, well, what are the actual coefficients that I need? So it was 2 for aluminum oxide and 3 for oxygen. So at that point, you're going to do some math, and it'll be a little different than some of the conversion factors you've used so far, because you're going to have to take 5 times 3, then divide by 2. whereas most of our other ones we've always had 1 is one of our numbers. So when you do that, 5 times 3 divide by 2, and moles of aluminum oxide is going to disappear. You are going to get 7.5 moles, and of course, what's our unit? Moles of oxygen. And that is our final answer, and we've got 2 significant digits, which we had 2 significant digits up here. Coefficients that you're using for your mole conversion factor are infinite. Okay, those are balanced equations, so they are considered completely 100% accurate. So this is our new conversion factor, and this is called molar ratio. The molar ratio conversion factor. Okay, all right. That is it for today. We will get into much more complicated examples on our next lesson, but you shouldn't have any trouble if you can just get this basic foundation down pat. Okay, thank you, and we'll see you next time.